Hi Security Tube, welcome to part 6 of the Exploit Research Megaprimer. Now in the last 5 videos, we've taken up multiple examples of buffer overflow attacks. Now that is the most vanilla, most basic buffer overflow attack which we took, and hope by now most of you who have been following the videos and trying the examples out by yourself are confident enough to write simple exploits for buffer overflows. Now we'll take up a slightly more complicated topic, which is SEH exploitation. Now SEH stands for Structured Exception Handler, and here we're going to look at a couple of other interesting ways to break into systems using this attack. So SEH requires a little bit of theory and background, and this is where in this video we'll try and understand SEH basics, take up an application in the end, and actually look at how we can navigate the SEH chain in a given application at any given point. And in the next video, we will look at SEH exploitation. So let's begin. So what is an exception? Well, very simply put, it's an event which occurs during the execution of a process, and this requires execution of some outside code which is not in the normal flow of control. What do we mean by that? Well, think about it. If your program has an error, then typically what you would do as a programmer is catch that error or catch that exception and then probably try and see if you can do some sort of an error control, right? So typical exceptions, there are two types. One is hardware based exceptions, which are examples would be a divide by zero, access to invalid memory location and things like that. And then you have software based exceptions, which is more of in the realm of application as well as the operating system running it. Now one common example is use of an invalid file descriptor, right? You probably close all file descriptors and then try to use it. So exception typically happens in the most common case, it's an error condition, and where we try to do some sort of a containment of that error. So what is structured exceptional handling? Well, this is a software method of actually dispatching and handling exceptions. Now, it is important to note that this was patented by Borland and licensed to Microsoft. And this is one of the very reasons why structured exceptional handling is not available in open source operating systems like Linux. The simple reason being it is protected by a patent owned by Borland. So, interestingly, SEH, the way it has been kind of architected, can handle both software as well as hardware exceptions, thus making it a very generic exception handler, and that gives it a lot of power because it can be applied to practically all cases. So let's try and understand some exception basics. So typically you would have a process in which you have some exception handling being done, like for example, in Visual C, C++, you would typically have a try except block, right? In try, you would do some operation, and if there is any error condition here, then if you have the appropriate exception handler set up using the filter, then the exception handler runs and the code within the except block runs. Now, as an example here, we've set up an integer pointer to actually point to a 0 address which doesn't exist. After that, we try and assign the value 10 to this pointer, to the memory location pointed by this pointer. Of course, this is going to go ahead and throw an exception, right? And at that point, basically what happens is, because this is an error condition, there is an exception which is thrown, which the operating system becomes aware of, and then the operating system figures out if there is an appropriate exception handler which has been created by the application for it. If an exception handler is available, then the operating system transfers control to that exception handler. Now this is a very basic flow, but now we will move into the details of how all of this works. So here's the first question. Well, it all seems quite natural that the operating system is going to call an exception handler. But the first question is, how does the OS actually locate the appropriate handler, right? This is where in any given process you could have multiple threads, right? In the most common case, you would just have the main thread, and every thread has what is called a thread information block, in which all information regarding that thread is maintained. Now, interestingly, the very first record there is basically the exception registration records, and the exception registration in the thread information block can be accessed using the FS register, right? So FS, and basically starting from the 0th location as the offset, we would be able to get the link to the exception registration records list. So this is a pointer pointing to this list, and every element of this list basically contains two variables, right? The first is the pointer to the next record. We'll come to what this means in a bit. And then the pointer to the handler, right, which is the exception handler. So in total, in the most common case, we basically have 8 bytes of exception registration record. Later on, we'll look at why this mechanism is also dependent on the implementation, and there could be other things also in the exception registration record. But we're definitely sure that at the very least we would have the pointer to the next record and pointer to the exception handler. Now let's look at how this exception registration record list looks like in a more complicated program. So I've kind of chalked out a very simple program with some exception handling. The main function calls function A. Within function A we have a try except block, and within the try block we call function B. Within function B, similarly, we have a try except block, and we call function C within that try block. And of course, there are more statements above and below the function C statement. Same thing applies to function A and B as well. And finally, in function C, we just basically print an SEH demo string, right? So let's look at how the the exception registration record list looks for this program. So most important thing is the registration of exception handlers happens at runtime, and this depends on exactly where we are in the program code. So what do I mean by that? Let's start with this program. So right now we are in the main function, and currently if you notice in main there are no exception handlers which have been defined, right? And we are in the previous line till before we have entered function A. So now this is how the exception registration linked list looks like. There is basically just one record, and the next pointer, which actually points to the next exception registration record, is actually all F's, and the handler is the default handler by the operating system. What do we mean by all this? Well, here is the thing. What if there are no exception handlers for a given application? What would happen, right? Someone would have to finally handle that error and resolve it. And this is where there is a default exception handler which is registered by the operating system itself when a new process is brought up. And basically, still when the process is starting, or probably if there are no handlers, this is the first record which is available in the program, right? And the exception registration list pointer in FS0 points to this record. Now the important thing to note is that all of these records are actually stored on the stack, and this is where, using a buffer overflow, we may be able to override this record. We'll come to the exploitation later, but please keep this in mind. Now from here we enter function A, and within function A, now our execution has entered the try block, and we are in the previous line before calling function B. So at this point, if you notice, there is an exception handler which applies to this try block, and hence this exception handler is going to get added to the linked list. And this is how the exception registration linked list will now look like. So what has happened? Well, the previous record which was there, which was the default handler, has now shifted and become the record 2, and the first record is basically the exception handler for function A, right? So now record 1 is basically having a handler for function A, and the pointer to the next record is actually pointing to the default handler, basically, which was actually from the operating system, right? So notice how we have actually added to the head of the list. Now, one of the interesting things you would notice is that the exception registration linked list is a LIFO, or last in first out. We'll come to how that works in a bit. Okay, now from function B we've entered function A, we've entered function B, and we are in the try block. So now the exception handler for function B also gets added to this list, and this is how the list looks like, right? So we have the function B exception handler and a pointer pointing to record 2 and the pointer pointing to record 3, and basically the handlers are in the order B, A, and the default handler. Basically function B, then function A, and then finally the default handler. Now finally, when we come to function C and when we are in the try block, basically now we would have an additional exception handler which involves function C. Excuse me. And this is how the registration linked list looks like, right? So what I'm trying to tell you is registration of the exception handler happens at runtime, and exactly where we are in the execution of the code dictates at what time which handlers are getting added to the list. Now, given this definition, it is natural that when the execution flow changes, various elements will also be removed from this list and new ones may or may not get added, right? So now let's look at what happens when we slowly return back from the code. So now we've printed SEH demo, it printed without any errors, and hence we have come back from function C to function B, but we're in the next line after the function C call. So now what should ideally happen is, because now function C is no longer in context, the exception handler of function C would be removed. And this is exactly what has happened, is that the record which was on the top was removed. So last in was actually the record for function C, and that got removed first. And this is the reason we call it last in first out. Now in the very next step, when we return from function B, function B's exception handler is also removed from the list. Similarly, when we come back to the main function, function A's exception handler is also removed from the list, and all we are left with is the default handler from the operating system, right? So some key concepts, once again let's quickly recap. The exception registration list is a linked list. The way in which the operating system can know where this list starts is by using the exception registration list pointer in the thread information block, and this is available by using the fs register and basically using fs0 as the starting point, right? Now the registration linked list will grow and shrink based on where we are in our program execution. As we enter more and more new functions or more and more code blocks which have the exception handler defined, our exception handler list will now increase in length. Once again, as we roll back and come back and return from many of these functions or code blocks, the exception registration linked list will shorten once again in size. And this is what we've seen in this entire animation, right? So we've talked a lot about the handler function. What is the prototype of this handler function? Now the prototype is defined in this file called exept.h, which is probably short for exception.h, and the return value is exception disposition. We'll look at it in the next video. And basically this is the prototype for the handler, underscore except underscore handler. You have basically a pointer to an exception record structure, and then you also have a pointer to something called the establisher frame. We'll look at this in detail in the next video. This is very important from an SEH exploitation perspective. Then we have a context record and a dispatcher context, pointers to both of these. Come to this. Now We talked about all of these records being created, deleted, and all of that. So the question is, where are all these records being added? The answer is, these records are actually being created on the stack. Now here is a simple program without SEH or structured exception handling, right? So we basically have a main program, function A, function B, function C, and in function C there is some printing happening. Now this is how the stack looks like for a program without SEH. This specific image and the next one has been taken from another source, which I'll mention in the end. So due attribution given to the great people who created such a nice image. Anyway, coming back, if you remember the buffer overflow primer, function A stack would have first arguments to function A, then the return address in the caller, which would be the main function, caller's EBP, which is the main function's EBP, and then after that you would have function A's local variables and other things. Similarly, now from function A, when we call function B, first we will be pushing the function B arguments, then we have the return address in function A, then function A's EBP, which we want to preserve, and then function B's local variables, and so on and so forth. Now in this case, high memory is at the bottom and low memory is at the top, so please keep that in mind. Now in a program which has structured exceptional handling, the stack looks a little bit different. What happens is, all the details of the SEH record or the exception handling record also now goes onto the stack. So this is how now the stack looks like. Inside function A, after the caller's EBP, we actually have our 8 bytes here of the exception registration record. Now the first 4 bytes, of course, if you kind of remember, is actually going to be the next record, and after that we have the exception handler for the current function, right? After that we'll have the local variables for function A. Similarly, in function B, we are going to go ahead and have the function B exception handler, then the next exception handler pointer, and then the local variables, and similarly for function C. Now if you remember, we had said that the exception registration records are all linked lists, and this is where, if you notice, we basically have this whole linked list given. So fs0, this is basically in the thread information block, points to the top of the list, and this is basically going to be in function C, and then the next registration record points to the registration record in function B, which in turn points to that in function function A. So basically C, B and A, and finally this record, though it's not shown in the diagram, goes back and points to the default handler or the default registration record which has been added by the operating system, right? So one of the important things which I want you to keep in mind is that the implementation of SEH varies. As an example, Visual C++ does not use the basic SEH we just saw. There are a little bit of other complications available, like scope tables. Basically, when you actually use Visual C++, there is a generic __ except _ handler 3 which actually applies to all exceptions, and then this function in turn, using the scope tables and a couple of other things, figures out which filter expression to call, and then finally, if the filter expression kind of gives a response that it can handle this exception, then calling the appropriate except block, all of this is actually done by this exception handler. So as an example, this is how the exception registration structure looks like for Visual C++. We have the first two, which you can kind of correlate, is a pointer to the next record and basically an exception handler function pointer. After that you have a couple of other things, scope table, try level and all of that. We will not get into these details because as far as exploiting SEH is concerned, we needn't worry about this at this point. So the good news is the implementation may vary. However, all implementations are vulnerable to going ahead and breaking the SEH and exploiting the SEH, right? Important thing to note is, in this simplistic picture, we immediately have our exception handlers after the previous function's EBP has been preserved. Well, in this case, the the pointers and their relative positions would end up varying depending on the implementation. Just wanted to mention this, keep this in mind that the implementation varies. Now a very good source to understand more about exception handling in Windows is a crash course on the depths of Win32 structured exception handling. Very old article published in 1997, but probably one of the most comprehensive and authoritative articles on this subject. The images were taken from this PDF written by Donnie Huebner on understanding SEH exploitation. This is also a very good article, you can have a look. So now we've kind of talked a lot about how SEH is applied and how the stack is going to look like and all that. So I guess I've bored you with enough theory, but this theory was very important. So now let's go ahead and do an actual demo to understand SEH in a better way, right? So please download the wonderful program from ExploitDB and we'll look at how SEH works. In this video, we will not look at SEH exploitation. We'll take that up in the next video. Demo time. So I'm going to be using Windows XP SP3 as always. And I've already installed the EasyChat server. So let me just quickly go ahead and open this up in Immunity. Let me make some space so that I can actually see what's there. Right? So here's what we will do. Let's kind of step through the program step by step to actually figure out how the exception handlers are working. So if I kind of correlate this with my slides, one of the first things which we said that by default we would have a exception handler which is registered by the OS, right? So let's step through the program step by step, started, and then look at the SEH chain, right? So the program has just started, but let's immediately look at the SEH chain. So one of the easiest ways is just to click view and then click on SEH chain. So if you notice right now there is just one SEH handler, right? And this is the address for the handler. Now if you remember from the presentation, we actually said that the address to the first handler is actually stored in FS0. So very simply you can just go ahead and in the memory location to the left, you can actually look at FS0. So you can just say dump FS0, right? And if you notice, this is the location where FS0 is currently pointing, and the next handler is actually coming out to be all Fs, which is exactly what we saw in the slides. So let's try to look at this also here. What we can do is, if you notice, the value stored in FS0 is basically 0012 FFE0. That is nothing but this position on the stack. And if you notice, it says end of SEH chain. Well, the simple reason is all F basically indicates that this is the end of the SEH chain, and the SE handler after that is actually that which will be taken care by the operating system. It is the default handler, right? So now let's move into the program a little bit more. Now note, we don't know the source code, but there are some easy ways by which you can figure out that the exception handler is being applied. Now one of the most common ways is basically this expression. So if you notice, we are actually moving the value of FS0 into EAX and pushing it onto the stack. Now this can only happen when we actually want to add another exception handler. So let's slowly step to this. Keep watching the stack here. You would notice the exception handler appearing here, right? Now this step is actually going ahead and changing the value of fs0 and having it point to the start of the latest exception registration record. Right? So I think it's kind of scroll by, but we can just quickly go up and have a look at this. So if you notice, this was the new handler which we just added. Now, if you kind of go back to the definitions, you would notice that what did we say? Well, we said the exception registration record is actually 8 bytes, right? Where is that slide? And the first thing we have on the top is the pointer to the next record, and after that pointer to the handler. So if you go back here, if you notice and draw a parallel, the first thing we have is a pointer to the next SEH record, and below that we have the handler for the current function in whose context we are currently running, or the core block. So this is how you can figure out what can be done. And if we kind of look at the SEH chain at this point, you should actually find two handlers in the chain. This is the one which is default by the operating system, and this is the one which we currently applied by running the application, right? So this in turn points to this. You can verify this. If you just go here, pointer to the next SEH record, and hit enter, it will just go ahead and follow this address. And at this address, if you notice, we basically have all F's, which signifies the end of the SEH chain, right? So, I mean, when a program is running, as we mentioned, the chain will increase in length, decrease in length, roll back to the default. Anything could happen. One of the easiest ways we can figure that out is to just restart the program and allow it to run. Right? So the program is all up and running at this point. And now if you view the SEH chain, you will actually notice that we have a couple of things, right? Of course, it ends with the default handler, which is something which we already know, right? The end of the chain always has to be the default handler by the OS. So here is something which we can do. We can actually go ahead and follow this address on the stack, open up, and this is the pointer to the top of the SEH chain. You can verify that by going ahead and once again dumping fs0, and you would find that this is the actual address where you would go ahead and get it, right? The address pointed to by fs0 is 0011EE98, and at that location 0011EE98 you basically have the exception registration record, right? And that record consists of these 8 bytes. So now you can actually navigate the whole SEH chain, and as they call it, walking the SEH chain by just hitting enter once. So now we are at the next SEH chain, and you can kind of verify this by just quickly looking at the SEH chains. If you notice, we were here, we've come here right now, right, FF08. You can once again hit enter to go to the next member in the linked list. You can hit enter once again, and this brings us to the end of the SEH chain, right? 4 elements were actually there here, or 4 members, as expected in what this is also showing us, right? So I think hopefully this example would have cleared up a couple of things. First, basically for SEH we require exception registration records to be stored on the stack. These records are members of a linked list. That linked list is actually referenced by fs0, which is present in the thread information block. We can walk that linked list one element at a time, and then we will always finally end up at the default handler by the operating system, or the default record, which basically signifies end of the SEH chain, right? Depending on where we are in the program flow, we may actually look at different exception registration records being added to the list and removed from the list, because registration of the SEH is actually a runtime thing. It's not related to anything related to compile time. Okay, so I guess this is all I had in mind for this video. In the next video, we will look at how to compromise and exploit SEH chains. So like always, I'm trying this new thing out where this whole picture-in-picture. Hope it is not very distracting. And please let me know your comments and any other queries you may have. That's all for this video. Thank you. And please leave your comments behind as always.